name is Sharma, and today Joseph Boylan and I have put together a STP analysis on maglev trains. So without further ado, let's get right into it. So let's go ahead and start off with a simple explanation of what maglev trains actually are. And essentially, the principle that magnetic levitation trains operate on is simple electromagnetism. And basically, they utilize powerful electromagnets and the basic principles of magnetism for propulsion. And a little fun fact, due to the magnetic propulsion, the trains actually float roughly 4 inches above the tracks. And this means that they never actually are in contact with the track. And since they're floating in the air, they can, with proper aerodynamic design, they can achieve very high speeds. So on this next slide here, we have a simple, image of a maglev train. And this is the SC maglev train, which is going to be a new maglev train opening up in Japan in 2027. And you can kind of see the superconducting magnets and so on and so forth. This is just a high-level overview diagram or picture. We'll go into more details on how the magnetic levitation trains actually work in the next slides. So now we will answer the question of how do maglev trains actually work. And essentially, they have a magnetized coil along the track that repel the magnets attached to the undercarriage of the train, and that's actually what causes it to levitate. Basically, the magnetized coils along the track repel the magnets underneath the train, and that causes the train to float in the air. And once the train is levitating, the electric current supplied to the magnetized coil along the track is alternated at a certain frequency, and this creates a periodic shift in magnetic field polarity. And this changing polarity actually causes the magnetic field in front of the train to pull the train forward. So it creates an attractive force in front of the train that pulls on the magnets inside on the undercarriage of the train, pulling the train forward. And behind the train, that alternating field actually creates a force that repels or pushes against the magnets that are underneath the train. And this actually propels the train from the front and the back. And that's part of the reason that they achieve such high speeds. So on this next slide here, we actually see a simple diagram of what I explained in slide 4 or in the previous slide. So on the left, we see the levitation of the train. So you can see how the magnetized coils underneath the train actually repel or push up against the magnets that are attached to the train's underside. And this causes the train to get pushed upward and to float some distance above the track. And I mentioned that was about 4 inches typically. Now, on the right, we actually see how the train is propelled. So basically, you can see that the alternating magnetic fields along the coil or along the track actually pull on the north pole of the magnet on the underside of the train. And behind the train, they actually push against the magnets. And so this, constant pushing and pulling that's produced by these alternating magnetic fields is actually what propels the train forward. Okay, so now that we've talked about what a maglev train is, let's talk about what are some of the positives. So the first one is that since magnetic trains operate on the concept of magnetic propulsion, they don't have a motor or an engine or anything like that. And since the propulsion system is electromagnetic in nature, there's no carbon monoxide or carbon dioxide emissions, and so it's very green. In terms of energy consumption, maglev trains are actually much more efficient than traditional trains, and once again, that's primarily the result of the fact that magnetic levitation trains float, and so they see less friction, and so it takes less energy to propel them forward. In terms of noise pollution, once again, the train has no contact with the track, and this means since it's floating in the air, there's very little noise, and so for people living around maglev trains, it's actually not as bad as it is for a traditional train. And in terms of the amount of land it takes to set up a maglev train network, maglev trains actually don't require as wide tracks. They only have a 12-meter wide dual guideway instead of the traditional 14 required for regular trains. So some additional positive benefits of maglev trains from a cost-benefit analysis, since once again the train floats and it doesn't actually touch the rails, the mechanical wear and tear of the different parts on the train happens much less quickly, and so therefore maglev trains have much lower maintenance costs than traditional trains. In terms of comfort, the absence of rolling friction on the tracks creates a very comfortable experience for the passengers. There's no vibrations, there's no loud noises, so on and so forth, and it's a very comfortable and smooth ride. Now, due to the way magnetic levitation trains operate, the chance of a derailment is actually very low, especially in most weather conditions. And once again, this is a result of the fact that the train itself floats above the track. However, the magnetic fields generated by the coil actually keep the train on the track. It makes it very hard for it to derail outside of very unique conditions or extreme circumstances. And finally, in terms of magnetic levitation trains have less weight dependency. For this reason, more space can be allocated to passengers with amenities such as sleeper and lounge cars. And this is a result of the fact that magnetic levitation trains don't need to stay mechanically attached to a track, right? They can float above the track. And this means that they don't need to be as heavy in order to ensure that there's no derailment. Like they have, like regular trains have to be a certain weight, or they have to weigh a certain amount in order to ensure that they stay on the track. Now, naturally, as with any technology, maglev trains have certain downsides. And some of those downsides include the incredibly high upfront costs for setting up a maglev train network. And in addition to that, there are health concerns. So, due to the presence of, strong magnetic fields required to keep the train levitating and to propel it, there's concerns about how those might have some long-term effects on the health of passengers and so on and so forth. And a lot of this is still being studied and understood. And the other thing too is we say that maglev trains are green, but they're green with an asterisk, right? Because if the energy or the electricity required to operate the maglev train is generated with fossil fuels, then that sort of defeats the purpose, doesn't it? And finally, with those high speeds that maglev trains can achieve, there's also high risk, right? We mentioned that the chance of derailment and other such things, except in extreme circumstances, is very low with maglevs, which means in general they're very safe. However, because of the fact that the train is floating and it's going so fast, in the event of a collision or a derailment, the amount of damage and the risk to human life is much higher just because of those high speeds and the fact that it's floating. So where are maglev trains currently being used? Right? Are there any commercial lines currently operating, so on and so forth? And in fact, currently in the world, there are 6 total commercial maglev trains in operation. There are 3 in China, 2 in South Korea, and 1 in Japan, with 1 more, with Japan expected to open up 1 more in 2027. And so you can see the technology is picking up in Asia, but unfortunately not as much in Europe or in the United States.
All right, hello everybody. My name is Joseph Boylan, and we're going to transition into different accidents that have occurred from the maglev trains and different hazards. So, the only known hazard to date is the one that happened in Germany, the Latin train accident. Now, it's important to note that this was not in commercial use. This was during a training run, and during this service, the vehicle ended up killing 23 people. Now, this is the first and only incident involving a maglev train that resulted in a fatal death to different individuals. So it's also important to note that this was a technological flaw, and it was based off of human error, right? As Sharma put it, who is an engineer specialized in transportation at the University of Kassel, he said that this was a human error and one should not have relied on human control in general, right? It's also important to note that there are different variations of this system in Japan that reduce the amount of human error, whereas the one in Germany decided against that. Hence, the result of this catastrophic accident. All right, after our continuous and extensive research on maglev trains, we discovered 3 particular hazards that we decided were the best hazards and most beneficial to elaborate on. The first one was unexpected power loss. The second was health concerns relating to individuals with pacemakers and how the external magnetic fields that are being outputted from the train can affect individuals with those pacemakers. And for the third one, if obstacles end up landing on the track itself. If you do a little research, you'll discover that many of the developers of these maglev trains and researchers from different universities have all concluded that these trains are almost entirely impossible to derail and can withstand almost all weather conditions, right? But on the off chance that an obstacle lands on the track that could potentially be extremely detrimental to the train, how can they avoid this hazard? So we're going to get into these three coming up next. For the first hazard we will discuss today is regarding if unexpected power outage occurs while the train is in transport, right? Maglev trains will still remain afloat even if electrical power is reduced. The electrical current is created between the oppositional magnetic field between the magnets, right? And that slowly is reduced when electricity is shut off, and it does not come to a complete halt very abruptly. And as it comes to a slow stop, the wheels on the bottom of the track or on the bottom of the train will glide with the track. As you can see the diagram onto the right, it shows if such an event occurs and how it is controlled. So for the second hazard, right, if a cardiac rhythm device such as a pacemaker comes in contact with an external magnetic field, could it potentially bring a disruption to the individual? So most modern day pacemakers contain a switch that closes if an external magnetic field around 0.9 milliteslas is applied to it. The switch then turns the device to a programming mode with asynchronous pacing. Now this isn't too worrisome, but it is something to be noted. And luckily, the field within or outputted from the maglev trains are around 100 microteslas. So it is extremely far from causing a reed switch within these devices. Of course, the makers of maglev still do recommend you see your cardiologist and get an approval beforehand. And it is worth noting that if your pacemaker is MRI safe, it is almost entirely perfectly safe to aboard these maglev trains. This is, of course, with the assumption that the train's magnetic field has been thoroughly tested. And that testing situation has been displayed on the right on the control diagram listed. You can see how the human operator in the control tower detects the magnetic field and determines if it is fine or if it is detrimental to individuals with pacemakers and how they will proceed forward. All right, so now for the third hazard, whereas an obstacle has now landed onto the track in which the train is moving on, how will the hazard be prevented? So there are current sensors and video cameras installed on all maglev trains that determine or detect if an obstacle has been placed onto the track and determine if the obstacle is severe enough to result in the train stopping or continuously moving towards its destination. As you can see on the right, it shows the process on how that is conducted. And on the left, you'll see from fellow civil engineer from the University of Kassel, Helmut, he said, any obstacle on a maglev train presents a problem. The heavier the obstacle, the bigger the problem. It's just simple physics. It's completely true. So even though most researchers and developers of the maglev train are extremely adamant that it's almost impossible to derail this train and that it can withstand almost all weather forces, there still is the possibility of an object landing on the tracks. And if that very rare situation occurs, there still needs to be a plan in place on how to detect and work around it. So one of the biggest aspects of the production for these trains is its autonomous features. So even going down to how it accelerates and decelerates, it is manned by an external control tower instead of having individuals within the train itself. As you can see on the right-hand side for this activity diagram between the control tower and the maglev train itself, and how it is determined to either accelerate upon departure or decelerate upon destination arrival, and how that is done thoroughly and safely. The socio-technical impacts that are involved within the development of this maglev train are nothing shy from complicated and extremely intricate. So it all the way goes down from who is going to be funding this project, whether it's going to be a government entity or private entity, all the way down from getting approval from the government in which it's being produced in. If the people where the town is being produced in actually approve of it, the infrastructure needed to go forward with it, right? So there's many aspects involved. We're going to use JR Tokai's Tokyo to Osaka maglev line, for instance. The people of Osaka were all happy by majority vote. They not only wanted the train to be developed, but they wanted to rush the process of developing it, right? So during the whole development process, the executives of JR Tokai were in meetings with government officials on a constant daily basis, going through production details, making sure that political entities weren't going to be a major influence in the process of its development, and understanding how they can use the fiscal spending of the government towards their own benefit, and if it would be a better idea to go with government funding versus private funding. So as far as the socio-technical impacts go for the operations of the maglev train once it's been properly developed, there needs to be constant feedback on all levels within the hierarchy. So the train itself needs to be providing constant feedback to the control tower. The utility company that provides electricity to the train itself needs to be providing feedback to the control tower as well. Now, this is extremely important as the control tower decides whether the train is accelerating or decelerating, if there needs to be any solutions or maneuvers to do if there is any sudden power outages. So constant feedback is extremely important throughout the entire system. Let's use the Shanghai's maglev train for a quick example. It is currently the world's fastest and oldest commercially used train in existence. It runs Monday through Sunday for majority of the day and has 6 maintenance checks that are around 15 to 20 minutes apiece, right? Now, this line from city to city has a separate track that takes it directly to the maintenance facility and determines if a quick maintenance check is sufficient, or if something needs to be fixed and the next trip needs to be delayed, right? The major benefit of using maglev trains in this situation is maintenance isn't as needed as traditional trains because of the lack of rolling friction that reduces the need for constant repairs and replacements over time, because the magnetic and electrical forces producing a levitational field for the train, the lack of rolling friction is an extremely beneficial aspect to the maglev trains and reduces the amount of maintenance and maintenance teams required to keep it up and running. So the future possibilities are extremely vast with maglev trains, especially in the United States. We need to break the chain of low expectations that we're currently dealing with maglev trains and realize that other countries like Germany and Japan are using these trains to extreme benefits, right? The whole purpose of maglev is to remove millions of people from their cars and fight climate change while doing so. There was a study done by NASA that showed the CO2 emissions in New York City from 2015 to 2019 and how it almost was reduced to around 95% during COVID, right? Now, this is not to say that the construction of the maglev line will completely remove the pollution in comparison to that of the COVID era in 2020, but it does show the improvement there can be with a significant amount of car reduction on the roads. So Maglev can 100% be a solution to this issue. All right. And it's currently known as the Internet of Trains, is a newly coined term. It's completely fully autonomous. And I think future possibilities of not only in the United States, but in Japan, Germany, and other countries, as technology becomes more evolved with artificial intelligence and machine learning, there will be more sensors, predictive analytics, and big data integrated into the Maglev system that could almost reach a 100% reliability rate, right? This type of central management system will maximize the amount of passengers, with operators only needing to simply alter the arrival and departure times, while the machine itself will take care of the rest. All right, let's get a little bit more optimistic and talk of the more future possibilities that are involved with Maglev trains. So there's current talks about Hyperloop technology and how that could force Maglev to completely change their system's current state of architecture. And this would only arise if more competitors came into the market, and once Maglev becomes the primary source of transportation around the globe, Hyperloop technology would more than double the world's fastest Maglev train in existence, which is the Shanghai line that reaches around 320 miles per hour. The Hyperloop would reach over 700 miles per hour. By placing it within a vacuum-style tube, the lack of air resistance would be able to help reach these feats. As for now, it's merely an idea. There's been a few projects that have been done globally that have shown that this is completely attainable. There is just some aspects, of course, financially and technologically that have yet to been developed, but people predict that this will 100% be the future of transportation.
So in terms of safety enforcement, or kind of what's going well, or how are these Maglev train companies sort of accounting for the different hazards present, it was notable the extent to which they've really thought about how to mitigate some of the hazards that we talked about in this presentation, and some of the hazards that we perhaps didn't touch on. As part of this presentation, we thought it made sense to include screenshots from some of the relevant sources so that we could make it part of the discussion. And so in the following slides, we'll go over some screenshots regarding the different safety features present on the newest Maglev train that's going to be in operation in 2027. But I want to note that these features are also present in some form or another in current Maglev trains. So without further ado, let's jump right into it. So here on this first slide, we see from SC Maglev's kind of safety brochure the different ways in which the train actually would come to a brake. And in the normal operation, the train utilizes regenerative braking, which is a common feature in this type of propulsion. However, in the event of emergency, the train can actually utilize aerodynamic braking to bring itself to a full stop. And in the event that the train loses levitation, it has those rubber wheels that we've talked about to kind of land safely on the track on, and it can utilize standard wheel disc braking to brake if it's in contact with the track. And so you can say the train has multiple redundant manners in which it can brake, and it has the ability to brake both when it's levitating safely and also when it's on the track itself. So both possibilities are accounted for. Now on this next slide, we actually look at how the train would behave in the event of an unexpected power loss. And you can see that they have accounted for this possibility as well. And in fact, that was one of the hazards that we touched on. And you can see that they have redundancies in place, including redundant power sources. So in the case that a particular substation suffers an electrical outage and the train is not able to receive power from that substation anymore, you can see that there are alternative substations that can keep the train propelled or keep the train levitating and keep that coil on the track energized. And as we kind of touched on as well, in the event that all substations go down or the power just isn't getting to those coils, the train does have those rubber wheels to sort of land on softly, and it can brake, as we mentioned in the previous slide, using the standard wheel disc braking that's common on most trains that have mechanical coupling to a track. So next we'll actually talk about a hazard that we didn't really cover, but what happens in the event of an earthquake or something like that, and the train starts getting vibrated or starts shaking, right? In this situation, you can see that even though the track underneath it, which is those magnetic coils, will be shaking because it's on the ground, due to the principles of electromagnetic induction, which are kind of demonstrated on this slide, the faster the train goes, the more the forces, the magnetic forces on it, actually force it into the center of the track and keep it on the track. So that's one of the reasons why maglev trains actually are very safe and why they have a very low chance of derailment. And when you compare this to a mechanical train, which the only thing keeping it on the track is its wheels and its weight, right? Instead of that reality with maglev trains, what you see is there's actually a magnetic force keeping the train on the track at all times, which actually gets stronger the faster the train goes. So now we'll take a look at gaps in safety regarding how safety is currently enforced on maglev trains and how these companies have attempted to address some of the hazards that we've already talked about. And it was notable that in the process of studying this topic, we did not really come across any major accidents other than the incident in Germany, which we discussed earlier. And that's notable for the simple fact that the oldest commercial maglev train in operation, which is the one in Shanghai, has been in operation for 20 plus years, and there have been no major incidents. And this fact kind of does align with the safety analysis done by engineers and regulators, where maglev trains are consistently shown to be significantly safer than standard trains. Now, despite this fact, maglev trains have seen very little adoption outside of Asia, primarily due to their high upfront costs and lack of regulatory certainty outside of Asia. One thing to note is that maglev trains are, as we have mentioned, extremely expensive to set up front, with one estimate putting the cost at $50 million per mile at the low end, and up to $200 million at the high end. And so you can see that maglev trains, require a significant upfront investment, and many countries have not been willing to put up with that high cost.
All right, as we wrap up this discussion on the STPA process used in the maglev trains, we're going to address some takeaways that we can apply. So as of going through this entire process, it's easy to see how much safer, more efficient they are in comparison to the traditional means of transportation that are used in the world at the moment. It shows how it can significantly reduce the CO2 emissions outputted by trains, taxis, cars, most forms of transportation that are used in today's day and age, right? One of the biggest things that we need to understand is that we need to break the chain of low expectations that most countries hold in talking about maglev trains. We need to understand that the short term might be expensive, but the long term will be extremely beneficial, right? And for that reason is the sole reason, as there's been many delays on these projects, is that the upfront costs are extremely expensive. The infrastructure creation is extremely elaborate, but it has been shown in Germany and Japan that the project does work long-term and is extremely beneficial to the people residing in those cities. We included 2 slides for the references that we needed for specific quotes, information, diagrams, and pictures.